Hello, good afternoon, everyone. I am Richard. I am a freelance deep learning developer, and I am really excited to talk to you at this afternoon at GPU Day about a topic that I think it's really important, and the title of The Importance of Randomness in Machine Learning. And this topic is often overlooked, but absolutely fundamental in the machine learning. So we all know that machine learning models are usually initialized and set with a specific random seed. So if we want to make our experiment or research to be reproducible, we have to use a random seed. But the first important question, when and where should we use those random seed to freeze the entire environment for our experiment? So, sometimes randomness occurs even when we use a seed. For example, initializing a new layer with Xavier uniform distribution. And sometimes there is absolutely no need to freeze the random because we want to create an application that fits the need for the real life needs. And there is a question, is it important to deal with randomness? And it depends on what and who we ask. For example, when we ask a theoretical scientist, they might say, yes, it's important because we have to freeze the environment and we have to make our experiment reproducible. But when we talk about a developer or somebody who create real-life application, they want to say, okay, it's not important because we want to create an application that generalized more than when we use a random seed. As a developer, I think both statements are clear and right. And it depends on in what stage we are. For example, if we want to test datasets and models, then we have to use a random seed. But when we want to train our final model, we have to use random values. So today we'll explore real-life examples demonstrating the importance or unimportance of random. And I try to show these examples from the perspective of a developer. And we'll look why it matters when it occurs the random and how to manage it effectively. And we'll cover specific use cases where randomness is either controlled or embraced. And finally, we'll examine broader consequences of mishandling the randomness. And I will talk a little bit about the quantum machine learning as well. So let's see. There are two major use cases when I mentioned earlier. The first one is the fixed random, and the second one is when we use the randomness. The first one is for reproducibility. It is for experiments only. For example, if a scientist wants to prove their results, they have to fix the random. There are a lot of scientific papers around the internet that is unreproducible. There are no code, but if they provide the code, they do not fix the random. So you are not able to reproduce those experiments. And it might happen that they ran a lot of experiments, for example, hundreds or more hundreds, and they choose the best one. It's possible because we are not able to examine the whole workflow. And the second one is the dataset validation. If you have a dataset, you have to validate. It fits for the real world well or not. So if it fits, then you can use a random values, and if it performs very well on a random values, then you can put in a real training process. And in this case, you can avoid any false positive results based on the random shuffling from the data sets. And you can verify the model structure as well if you use random. But when you don't use random, it's for real life scenarios. You can provide noise with the random values. For example, in this presentation, I use artificially generated images. But the most important thing that I put only 2 prompts in the generative AI. But you will see a lot of different images. And the difference is random only. So I think random is important. They help to generalize models, and they help you to get out the local minima. And let's see where randomness happens. Randomness can happen when you initialize a model with layers. It can happen in weights and bias as well. It happens when you shuffle data sets. It happens when you use a dropout. And if you use a floating point operation, it's important because I think most of you use floating point operations in your work. And there is a random in those operations. If you're using pooling layers in a machine learning model, those are unreproducible. And in a web propagation process, it happens random as well. But when we are see this problem on a different level, random occurs on the operation system level as well. It occurs on the Python level and library level, for example, NumPy, TensorFlow, PyTorch. And it happens on the hardware level as well. So if you want to freeze the environment, you have to deal with all of those. Let's see some. CUDA. Yes. This is the toolkit of the NVIDIA company. It is made for create machine learning operations on GPUs. And the OS means operation system. So let's see the basics. Python. You can set the random, importing the random library, and set random.seed, and you can use your favorite number. And if you move a step further, we can set on the PyTorch level as well. Import PyTorch and torch.manualSeed 0. It's okay. But if you use TensorFlow, we have to use another command. TensorFlow.random.seed. But TensorFlow and PyTorch works with NumPy. So if you set a random seed in TensorFlow and PyTorch, the results will be unreproducible because you have to set the random seed in NumPy as well. So numpy.random.seed. And we can move a little bit further. If you want to use a script that runs in multiple processes, you have to set the operation system random as well. But it works only if you use different processes, because the random is initialized when the IPython console begin starting. So if you start your Python program, then you set the OS environment variable, it has 0 effect because the random comes from an earlier stage. So if you want to freeze your environment, then I advise you to set the random and run your process in a new process. And you might want to split your data set. Most of developers use sklearn. And there is a random state as well. But if you want to train on a CUDA device, you have to set those variables as well. The first one is interesting because it's a benchmark. And why is benchmark important? Because it provides just feedbacks to train faster. And this is the problem. Because CUDA tries to control everything in your training process. It chooses the best algorithm that provides the fastest result. So you have to set it false. And in that case, CUDA will set only one arithmetic operation and one algorithm. So your experiment will be reproducible. But when you are training with Torch, you have to set the deterministic algorithms as well. Because there are a lot of algorithms that are unreproducible. And in a latest CUDA versions, you have to set the workspace config as well. It's just a memory pool and the number of workers. But if you set those values, then CUDA will use predefined memory and the number of workers. So if you say, I want to use 2 workers, then CUDA will use only 2 workers during your training process. And what happens when you want to use a PyTorch data loader? You want to load enormously huge databases. Then most of you will use different workers. But if you initialize different workers, then each worker will have different seed. So you have to create your own init function. Yes. So you set a random seed and define a function to create new workers. And that function, you can use the seed value. And in this case, if you create, for example, 9 or 10 workers, all of them will use the same seed and all of them will work the same. And there is a trap when we are talking about randomness. For example, we can use unshuffled datasets. It's okay, but it leads towards converge and word generalization. If we fixed the initialization process and random, it can lead that to logged in a suboptimal local minima. And when we split our datasets and test and train datasets without random, then those sets will different in each RAM. So you might get a good result, but you won't know why. And where things can still go wrong. For example, CUDA use non-determinism, and if you use CUDA devices to train, and then CUDA will use different algorithms to optimize your training process. So I showed those functions, but in real life, you won't be able to control your training workflow. So if you want truly reproducible process, then you have to use CPU only. A floating point math order not guaranteed across hardware. So if you put your model from the general RAM into the GPU memory, then those floating point operations that happen in the CPU and on the GPU will be different. And it can happen when you load your dataset. And if you use specific layers. So what can you do? You can set random seeds globally. So I advise you to set all of the possible random seed. For example, on Python level, operational system level, NumPy level, PyTorch level, and CUDA level as well. Use deterministic algorithms. There are a lot of layers that are deterministic. For example, linear or dense layers. There are layers that might be deterministic. Those are convolutional layers. For example, PyTorch says convolutional layers are deterministic, but CUDA says those layers are not deterministic. So it depends on who you believe. So, and avoid implicit randomness. For example, you can save the initial model state. You save the model and you can load in each iteration. For example, if you create an experiment in the morning, then you load in your model. And if you want to use another experiment with different hyperparameters, you load your model again. In this case, the model will be the same. You can save the dataset as well. Because if you use different workers with the fixed random, it might happen then the workers load the dataset differently based on the operation system level. Why? Because those workers try to reach the file on your SSD or Winchester. And it might occur that some file is not available at the moment. So the operation system will load in later. In this case, your dataset will be different in each RAM, even if you set the random state. And be cautious of library version changes, because sometimes if you use a newer library, a newer version, it might deal with different random. So I advise you to freeze your whole developer environment. For example, if you want to use PyTorch 2.1, then try to create your whole experiment with that version. And there are implications in research and production. For example, false sense of model performance from lucky runs. 4 years ago, and a funny thing happened in my work. I worked with 10 colleagues, and we got a really good result after each run. So we tried to train our model, and the first run was absolutely fantastic. And one of my developer colleagues said, okay, we get a lucky batch. It was a lucky train. And the other colleague said, is lucky train a technical term or what? No. And we just laughed because it was absolutely luck. And when we tried to retrain the model for 20 times, the performance will be better. But we tuned the hyperparameters. But for the first run, it was impossible to reach that performance, and we were just lucky. Troubleshooting becomes harder. If you do not freeze your environment, it's impossible to fine-tune your hyperparameters, because you won't know the cause of the good or a bad result. It can come from the data in the batches, the order of the data. It might come from the initialization. Everything can happen. So in production, random matters. If you want to create an application that works in real life scenarios, in real life use cases, then you have to use random values. And there is an important thing, the European Union AI Act. It's a regulation that regulate all of the AI models that is developed and used in the European Union. And it said you have to develop a model that is transparent. And you have to provide a whole workflow, a data workflow, and you have to say that I use those data points, or my model process some modifications on that data, and the result is this. And it's impossible if you do not use random seeds during your training. And what about quantum models? The quantum systems are inherently probabilistic. But let's see, PennyLane. PennyLane is a quantum model framework. You can initialize your quantum qubits with different random. For example, NumPy. Or you can use the entropy of the operation system. Or you can provide a function, a JAX function. All of them can work, but you have to choose one of them. If you don't choose, then PennyLane will use the NumPy random. So in this case, if you want to use PennyLane, you have to set your random seed in NumPy level as well. And the most important thing that simulators might work with different random compared to real life. For example, if you want to use a truly random number during your simulation, those are not real random. Those are just pseudo-randoms. And there are some key takeaways. So, for example, randomness is essential in real-life scenarios, but must be managed. So, if you want to experiment about the data set and your model structure, then you have to freeze your environment. But if you want to train a real-life working model, then you have to use random values. Reproducibility is hard. So it's not a binary thing. So it's not that, okay, I create a script and it's reproducible. It might not. But we have to do everything that our experiments will be reproducible. And we can use explicit seeding across all levels if needed. For example, Python level, operation system level, and the library level as well. And the most important thing from the quantum machine learning, that quantum machine learning highlights randomness as a feature, not a bug. And do you have any questions?
So thank you for your talk. I'd like to have a technical question. When you read NumPy's documentation, they advise against setting the random seed, and they say that you should use an RNG generator object and pass around that. Could you comment on that, what that means?
Yes, it depends on your use case. Most of the time, I advise you to use that NumPy random. But if you want to use a scientific experiment and you want to provide your code with your paper, then you can follow the the suggestions of the developers. But it depends on your use case. Most of the time, this example works very well.
You have checked what are all these default seed values. They are, I guess, then not all 000 from everybody, from all the different packages, because then that would be a clean situation that by default, if you don't touch anything and don't set or reset, then everything is seed 0 everywhere. But this is not the case, right?
No. If you set the 0 in all library, 0 means 0 has different meanings in each library. But it doesn't matter because you freeze your environment. So it will be reproducible. For example, it might happen that the same process in NumPy and PyTorch needs different random seed values. But it's okay, because if you use a strict number, then if an other developer will use that number, they can reproduce your results as well.
I think some cautious approach is unavoidable, because sometimes when you set all of the random numbers, it's your computer, it fixes the environment. But if you do it, so deploy it and sell the product to users, they might mean a different thing in the user's computer. So that maybe that's why that there are so lot of unreproducible results in AI. Maybe that is one of the aspects that the randomness is set differently.
Yes, you are right, because random can occur on the hardware level as well. So it's impossible to avoid this scenario. But we have to try to deal those problems as well. So if we set all of the possible random state to a fixed value, then it is the most that we can do. And I think it's enough.
May I have another question? So then let's set these seeds in an exact experiment or a prediction, or I don't know, some accuracy in terms of the actual data of the run with one model. How much change that would cause if, instead of 5, you set another seed, or but you do set them, but whichever you need, you do set the seeds. But from one experiment in another one, you set some other seeds. So in an exact prediction or in whichever exercise, what could be the difference?
The difference can be really wide. For example, there are, how to say it correctly and polite, there are tricks to deal with random. For example, there are data sets on the internet that provide random values for your experiments. If you use that random values, you will get a good result. So you can fake your experiment based on a random number. And I think this is a really hazardous thing, but from the perspective of a developer, we have to try to make our code reproducible. Because if somebody create a scientific paper and put on arXiv or Nature, doesn't matter, without code, it's impossible to reproduce. But sometimes they provide a link for a GitHub repository, and it do not contains a random seed. Then, for example, if I run that code, I might get a different result.
So thank you for your presentation.